Okay, this time I'm going to be working in section 2.2. I'll work through problem number 56. In problem 56, we're given the fact that f of x equals 5x squared, and we're asked to find the derivative of that function at x equal 10. And we're asked to find that algebraically. So in order to find the derivative of a function, what we're really looking for is the instantaneous rate of change right at that point. And so we're going to use our difference quotient, which tells us the rate of change. So I have to take f at 10 plus h and subtract f at 10. That's the change in my outputs, and divide it by the change in my inputs, which is this value h. And because I want the instantaneous rate of change, I need to take the limit of all of that as h approaches 0. So in other words, as that space between the inputs gets smaller and smaller and smaller. And all of this is going to give me the derivative of the function at x equals 10. So I'm going to squeeze that in there like that. Okay, so now I'm asked to find this algebraically. So the first thing that I need to do is I need to say that I need to work with the function that I've been given, 5x squared. And so changing now from function notation to the actual formula for the function gives me the limit as h approaches 0 of, let's say, the function at 10 plus h. So that's 5 times 10 plus h quantity squared minus 5 times 10 squared. That's the change in my outputs all over h. Okay, so now what I need to do, and all of that is equal to, make sure you're using the right notation, by the way, as you go through here. You can't just start dropping off the equal sign, the limit notation. We're still looking for the limit of all of that as h approaches 0. So I need to make sure that I'm being consistent in what I'm doing. Maybe you need to go off to the side to do the 10 plus h squared, but remember 10 plus h squared means 10 plus h times 10 plus h. So I distribute the 10 first, and that gives me 10 squared, which is 100. Distribute the 10 again, and I have plus 10h. Distribute now the h, so that gives me another 10h. And distribute the h again, and that gives me h squared. So from all of this, I get 100 plus 20h plus h squared. So let's go back and put that in. So the derivative of the function at 10 is equal to the limit as h approaches 0 of 5 times 100 plus 20h plus h squared minus 5 times 100 all over h. And now I'm going to distribute my 5s. So all of that is equal to the limit as h approaches 0 of 500 minus, plus 100h plus 5h squared minus 500 all over h. I'm going to clean this up a little bit. I see that 500 minus 500 would become 0, so that becomes eliminated. So I have the limit as h approaches 0 of, and I'm going to just reorder this a little bit here. And I see that I get, sorry about that, got a little distracted for a moment. And I see that what I have left is 5h squared plus 100h all over h. Now I can do a little bit more cleanup algebraically. And I see that what I have here is the limit as h approaches 0 of the 5h squared over h leaves me with 5h. 100h over h leaves me with 100. So now I'm taking the limit as h approaches 0 of this expression right here. Okay, so now let's actually take that limit and let's see what that is. So the limit as h approaches 0 of this expression here, well, let's think about what happens. As h gets closer and closer to 0, 5 times h is going to also get closer and closer to 0 because 0 times any number is 0. So the limit of this first term here is 0. And then, of course, as h gets closer and closer to 0, that has no effect at all on this constant value here. So the limit as h approaches 0 of this expression is simply equal to 100. So I can say that the derivative of this function at 10 is equal to 100. Notice I've taken the limit. When I did that last step, I took the limit. So the limit notation is no longer there because I have taken the limit. And I've come up now with my final answer.